Okay, so today we're going to talk about special right triangles, and the whole focus of today is to try and give you guys a shortcut, things that you can memorize so that you don't have to do the Pythagorean theorem all the time when you're trying to figure out sides of right triangles. We've already talked about a couple of right triangles, stuff like the 3, 4, 5 right triangle and the 5, 12, 13 right triangle, things that you can memorize so that you don't have to do the Pythagorean theorem. They're very common. And also we've talked about multiples of those sides. So if you've got a 3, 4, 5, that's, you know, there's also multiples of 3, 4, 5, like 6, 8, 10, 9, 12, 15, that are also going to be right triangles. But today we're going to look at it from a little bit different point of view. We're going to look at angles. So here's the two we're looking at today. A 45, 45, 90 triangle. So we're going to sketch one. We're going to indicate the angle measures and the side lengths if one leg measures 1 inch. Okay. So a 45, 45, 90 right triangle would look like this with its angle measures. Okay. Now, if one of the legs is 1 inch, well, this is an isosceles triangle because if these all opposite angles are congruent, then these opposite sides are congruent as well. So if this side's 1 inch across from a 45-degree angle, then this side is also going to be 1 inch because it's across from another 45-degree angle. Okay. Now, as far as the other side, we've got a right triangle. We know two legs. We could do the Pythagorean theorem. We could figure out the third side. Leg squared plus leg squared would be hypotenuse squared. So the hypotenuse is the square root of 2 inches. That's exact. We're not going to bother turning that into a decimal. Now, this relationship is going to be true for any 45, 45, 90 triangle. And I'll explain what I mean here in an example coming up. Now, the other special right triangle that we want to deal with today is called a 30, 60, 90 triangle. So we're going to sketch it. Okay. And it says to indicate the angle measures and side lengths if the shortest side is 1 inch. So if we've got a 30, 60, 90 right triangle, the shortest side would be across from the smallest angle. So it'd be the 1 inch, okay? Across from the bigger angle, some might think that, oh, well, it's twice as, the angle's twice as big, so this side's got to be twice as long, but that is not true. Here, I'll prove it to you, and then we'll go from there. Now, what I do know that is a 30, 60, 90 triangle is half of an equilateral triangle. Let me show you what I mean. Okay. Oops, that should say 30. Sorry, let's fix that. All right. 30. Okay, so we got 60 up here, 60 down here, and 60 down here. All right. So if those are all 60-degree angles, I could assume that this is also a 1 inch side, making the entire bottom 2 inches, which would make this entire side 2 inches, okay? Because this is a congruent triangle to this green one. So 1 inch bottom, 1 inch bottom. That means 2 inch base. And in an equilateral triangle, or an equal angular triangle, same thing, all the sides would be the same. So if this is 2, then this left side would be 2. So it's not this side, this leg that's 2, but actually the hypotenuse is 2. Okay. Now we can do the Pythagorean theorem to figure out this other leg. We can go leg squared 1 squared plus the other unknown leg squared equals, and that should say 2 squared. I'm going to fix that right now. So b squared must be 3, and b would be the square root of 3 inches. Okay, so the idea here is that we want to try and memorize these two triangles. A 45, 45, 90 triangle, it would go leg 1, hypotenuse square root of 2. And for a 30, 60, 90 triangle, it would be 1 square root of 3, 2. All right, here we go. What are the approximations for the square root of 2 and the square root of 3? Well, square root of 2, I'm just using a calculator. It's about 1.41. And the square root of 3 is about 1.73. Okay. So how many units is it from the origin to 2, 2 on the coordinate plane? Let's make a little sketch here. Here's my coordinate plane. I'm going to make a point at 2, 2. Right here. Okay, and we're trying to figure out the distance from the origin up to that point. So that red dotted line is what we're trying to figure out. Now, I formed a right triangle here, but it's also an isosceles triangle, which means it's a 45, 45, 90 triangle. Remember, it's supposed to be 1, 1 square root of 2 for the hypotenuse. So shouldn't, if I double the legs, then the hypotenuse should be double as well. So it should be not square root of 2, but 2 times the square root of 2. So there's a 45, 45, 90, 1, 1 square root of 2. So if I take this 2, 2, this would be 2 times the square root of 2. It just should be twice as big. So the 0.22 is 2 times the square root of 2 units from the origin. Now, using the square root of 2 up here is about 1.4. 2 times 1.4 would be about 2.8 units. It's not quite 3 units. If each side of an equilateral triangle is 2 inches long, then what is the area of the triangle? Each side of an equilateral triangle is 2 inches long. And what's the area? Well, I would need to know this height right here. Well, think about that 30, 60, 90 triangle we just drew. Okay. If we drew the height straight down, that would cut this into a 30-degree angle, and this would be a 60-degree angle. We have a 30, 60, 90 triangle, which means the shortest leg is 1, the hypotenuse is 2, and the height is the square root of 3. So if we're going to figure out the area of this triangle, we need to do 1/2 base times height. 1/2 base times height. So we're going to do 1/2 of 2 for the base, and the height is the square root of 3. So it would be the square root of 3 inches squared. Remember, off the previous page, we said the square root of 3 is 1.73, so it's about 1.73 square inches, just a little bit less than 2 square inches. A regular hexagon has sides 2 feet long. What is the exact area of the hexagon? And what is the approximate area of the hexagon? Well, the exact area would be, well, if we could find the area of this one triangle and then multiply it by 6, we'd have the area of the hexagon. That, since it's regular means that all the sides are the same. So that blue triangle right there is square root of 3 square feet. We just found the area of that triangle on the previous slide. It was in inches over here, but now we're working in feet. So we'll just, we just did the work, square root of 3 square inches. So square root of 3 square feet. Why repeat our work? And so the area of the entire hexagon would be 6 times that. Sorry. Area of the hexagon would be 6 times that. Total area. 6 times the square root of 3. That's the exact area of the hexagon. The approximate area we could find by doing, instead of 6 times the square root of 3, 6 times the square root of 3 is about 1.73. So that's about, using the calculator here, 10.38 square feet. Okay. So what we did is come up with some ratios for these common or special right triangles. 1, 1, square root of 2 for a 45, 45, 90. 1 square root of 3, 2 for a 30, 60, 90 right triangle. And then we use those to kind of make our work a little bit easier. So I'm just trying to give you a shortcut, and we'll perfect this by using it very slowly and surely over the coming days. Don't get freaked out. You don't need to be a master of this yet. All right. I'll see you tomorrow. Good luck.